Our homework last night was the remainder of page 467. We had done questions 1 to 5, and we checked over some questions there yesterday. We assigned questions 6 to 13 for today. Any issues with any of those questions on page 467? No one? 6? Okay. Next. Yeah, Julia? 7 and 11? All right, 6, 7, and 11 it is. Oh, here's a good question. Using the concept of impulse, explain how a karate expert can break a board. That's the key. Okay, we look at this sometimes and think, oh, we want to increase the stopping time. Decrease the stopping time to increase the force. And that's a perfectly logical explanation for this, right? Perfectly logical explanation. Okay, it's a good thought process, but it's not what they actually do. I'm not a karate person, so bear with me on this. But the way I understand the way a karate person looks at this is that they kind of look at a place behind the board. So if they're trying to hit the board, they're imagining a place behind the board. Does that make sense? You're looking behind the board. And then when you raise your hand or your heel or whatever it is that you're breaking the board with, you're trying to hit that place behind the board. So what happens when you do that? When you're trying to imagine hitting that place behind the board, you're actually increasing the time, following through, right? It's like swinging the baseball bat or the golf club, you're following through. Okay? Think about it this way. You're not trying to stop your hand. You're trying to start the board, right? You're trying to start the board moving. Does that make sense? Because you're trying to start the board, it's not a predetermined impulse. You want to give it as much impulse as possible. Think of it this way too. If it was simply a matter of decreasing stopping time, increasing force, breaking the board, Newton's third law says a reaction, there's an equal and opposite reaction. You might break your hand too, right? So what you want to do is increase the impulse to the board with hitting it as hard as you can, but without increasing the force to the point where you're going to break your hand there. Yeah, go ahead.
Oh, sorry. I just wanted to, like, ask a question. If you didn't use it as impulse forcing, could it also force on precedence?
No, I don't think so. Not in this context, at least. The question was, if you didn't hear, guys, was about resonance. It would be conceivable to break something. I don't know about a board necessarily, but it's conceivable to break something using resonance if the force is applied at the resonant frequency of the board. The disturbance starts growing and growing and growing. I'm not sure that a board would, like a short board like that, I don't think you would end up breaking. It would have to have quite the force at the resonant frequency. Probably not as big of a force as the karate expert is applying, but it would still require a pretty big force, I think. A piece of glass would be different, right? It would require a lot less force at the resonant frequency. So I think you might be able to tie that in, but it would be probably a stretch, yeah, probably a stretch. So the bottom line is here, the karate expert's looking at the point behind the board, and they try to hit that point behind the board, and the whole point of that is that they're following through. So it's increasing the time of contact. And when we're increasing the time of contact, we're not trying to decrease the force, we're trying to increase the impulse imparted to the board, and therefore make the board move more and right. Make sense? Anybody have an answer kind of like that? Okay. Good. Next question was number 7. Number 7 says, from the graph below, what is the magnitude of the impulse provided to the 48-gram tennis ball that served due south? Okay, air equals impulse, right? One more thing there. If you can actually see the entire graph, the time is in milliseconds, right? Be careful with that, especially when it's on a graph. Let's find the impulse here. We're going to say the impulse is the area And that's simply going to be 1/2 base times height because it's a triangle. 1/2 of the base, which goes from 0.5, it looks like, to 5.5. The base is going to be 5 times 10 to the minus 3 seconds. The height is going to be, what, 900? What is it, Fraser? 2 point. Exactly. 2.7 Newton seconds. All right, now we want to find, that's A, we want to find the velocity of the racket or the ball when the racket and ball separate. So we're going to say delta P is equal to M times delta V. We're going to say delta V, I think it start at rest. It doesn't actually say, I think we have to assume that. So 2.7 over 0.048 or 48 times 10 to the minus 3 gives me my answer. All right. That's it for today, guys. Have a good weekend.